Okay, so firstly, any questions on the homework? No one's got anything? Okay. Again, there are some jumper wires out here, so connect. Oh, you're attending too? Welcome. So actually, sorry about the snafu yesterday. I had forgotten that I was going to use 2 successive Fridays to do the lecture. So basically, Tuesday we'll have a 2-hour discussion section so that Amr can go more systematically over things. 50 minutes turns out to be very rushed. So make sure that you attempt the homework prior to that, so that in case there are questions, he can kind of answer it. But again, in the interim, obviously, Piazza is there. While it is easy, I think, but also many of you don't have the background necessarily, so make sure to start early, particularly if you have never done embedded programming. So to recap, what we started doing last time was to go through timing constraints and how do we schedule multiple tasks. On the timing constraints, there were a few things we covered. First was who the constraint is on. So constraint on the computer versus on the environment, right? So one is saying about performance, that you as a designer, hardware, software performance, you have through some hardware, software tricks, you have to meet that performance. And on the environment means that you are going to place some constraints on the environment, and if the environment doesn't behave that way, then all bets are off. So otherwise, it is pretty hard to kind of meet any sort of constraints, really. So that was one thing. Then the other dimension we had looked at was the type of constraint we had, namely, was it a max constraint, min constraint, durational constraint, and then we had this category of more complex, which kind of involve multiple events and all. So max basically places some sort of a constraint on the time elapsed between 2 events, cannot exceed something, and min says that it cannot be less than something. And then we had this notion that given a system or the environment, their input is what we call a stimulus, and output is a response, right? Input, output. And what happens is the response of the system is really the stimulus to the environment, or at least one of the stimuli to the environment. There might be other things like humans and all, but we can think of them as part of the environment, really. And then what comes out of the environment is what feeds back into the stimulus. So we have kind of this kind of a loop structure going on. And then we have talked about how, from the perspective of any one of these, or from the perspective of our system, which is what we're interested in, we can have various kind of constraints. We can have SS, which is constraint between 2 stimuli to our system, and they can be both max and min variety. So just to refresh our memory, can you tell me an example of each one of these constraints? So from our computer system, what might be an example of where I'm putting a max constraint on 2 input events? That is, we want the stimuli those 2 events to happen no more than certain time apart. Yeah. Yeah. Right. So I would place a constraint on some other computer or human feeding events to me, and I'm basically saying that they should arrive in a certain time, because if they don't, I will time out. So during the lecture, I had the example of the human being who might press one button and then wait forever. So obviously, computer can't, it doesn't make sense for it to wait forever, we'll lock the thing out. So that's an example of max. Minimum, yeah, do you think you can come up with that? So some example where we are going to say a minimum constraint on. Yeah, but can you translate that into a minimum constraint? So we're basically saying the event should be at least that far apart coming in.
Like, for example, if you have a keyboard connected to like a screen, right? You don't want the user to, like, let's say, a robot and then press the key like 10 billion times.
Yeah, your CPU may be too slow for it, right? For example, right? I mean, if I press it too quickly, while still processing the one interrupt, the next one came in, and next one came in, so there will be overload there, right? So this would be an example of to avoid interrupt overload avoidance, and this is some sort of a timeout. And we had SR, RS, RR. I would like to kind of go ahead and kind of think about these different scenarios, but that's what we have. Now, in certain parts of CS and E and the embedded systems we design, we do worry about all these constraints, okay? Particularly when you are designing interface logic, device drivers, glue logic, which sits around your processor, things like that. But when it comes to scheduling, we adopted a simpler model. And that simpler model, let me create another page. So for scheduling, simpler model. And the simpler model we had is that we have a bunch of tasks. Think of them as handlers for events. So we had bunch of tasks, tau 1 through tau n, and they had associated with them periods, t1 through tn. And the periods are really a function of my application. So I can't say that if I have a faster processor, then the t's change. They don't. T's are defined by the physics of the environment. For example, T may be decided by, if it's a sensor, we are sampling it, so sampling rate. And what is sampling rate dependent upon? Frequency, recall from a couple of lectures ago. And frequency is really saying something about the characteristic of the signal, right? I mean, human voice has certain part, covers certain part of the frequency, acoustic frequency spectrum, so that dictates how we are going to sample it. So this is function of environment, right? It's decided by the physics of the app. Then we had another thing which was kind of I had called it the phase, but which is really arrival of the first instance of a task. So remember, each one of these tasks, they fire repeatedly because they are acting upon a stream of events corresponding to the stream, right? So what we are saying out here is we don't know this. Because if we knew it and we have already assumed that the tasks are periodic, then that means that for that task I know the arrival time of all instances for future, and then you can just solve the problem statically, right? So this unknown makes things interesting because that means after my system starts up, it has to be prepared for all the eventualities. So when we say that when the operating system says, I will be able to schedule this task set, it's making a promise that for any value of the arrival of the first thing, it would be schedulable. And then finally, we had the compute time. And in particular, we had the worst case execution time, often called WCET, WCAT, and that we had it as C. Now, this is obviously a function of CPU. So I can CPU frequency and CPU type, right? Same algorithm on different processors may take different time, and for the same processor with different frequency may take different time. But we had also talked about that how the reality is more complicated because data value dependence was one factor, cache effects, and power management. All of these things, sort of in various ways, make this value c, or c sub I rather, to be variable. Okay, so but somehow we still kind of assume that we know that magically kind of the worst case one. Presumably you will do it by profiling, but there are also CAD tools which can take your program code and knowing which processor you're going to run on, they do some analysis, much like similar tools exist for digital circuits where they can predict clock speed. Okay, it's very similar problem. You're trying to look through all the possible pathways to the code and trying to identify which one will take the longest. Okay, so that's our model, and at least to begin with, we also assume that they're independent. So with all those assumptions, and some of these get relaxed in theory, some of these we don't have the theory to handle it, but there is sufficient richness overall that these are very practical sort of tools to apply. So with all of this, then the other thing we had said was that the type of model we are going to assume is that tasks are preemptible. That is, the OS can bump off a task, and they have a priority. And we talked about how Mbed OS does provide a notion of priority. In case of Mbed, the preemption can only happen at certain points, so it's some more restricted model than the theory that we are talking about. But there are other operating systems, free operating systems, which have ability to preempt arbitrarily. Okay, so with all of that, then another concept that we had introduced was that if I am so if my problem is that the question we're asking is, can I schedule it? And given the model we have of this priority, and the OS is always running highest priority tasks, highest priority ready task. So with that, our scheduling problem is equivalent to the problem of assigning priorities. And in particular, we are going to assume static priorities. So our model is known number of tasks, and they've all been given priority. And now the question comes up really is, you can think of the following question we are asking: schedulability. Can I schedule it? That's equivalent to saying, can I find a priority assignment which won't result in any task, any instance of any task missing deadline. Oh, I forgot earlier that the deadline in our case is DI is the same as DI. Okay, so we just wanted to finish before the next one. So that's really the question we are asking. And then I threw a intuitive couple of examples. We have shown that it appeared that lower the time period for a task, better it is to it's better to assign it a higher priority. So given two tasks, it appeared always that if I were to give higher priority to the more frequent task, I'm better off. Okay, either I could schedule it and not the other way around, or I would have a more flexible schedule. So that led to the concept of rate monotonic, which is basically saying priority proportional to TI inverse, right? So the rate. So the result, again, we didn't prove it, is really that if RM cannot schedule, that is RM priority assignment, then no other static priority assignment will work. So that was a powerful result. Yeah.
Is Ti the number of times?
Ti is a period, right? So successive arrival of the like sensor samples coming in. What's the period of those data arrival?
With respect to tasks, how is it measured?
So think of this way: every time a sensor sample comes, I spun a new a thread which will run a function and exit. That's one way of thinking about it. The other way of thinking about it is in my thread, I have a wait statement. So I say wait for the sensor samples and then do some computation and then go back. Okay. So what TI is saying is that the sensor samples are arriving every TI. Either case is sort of, I think probably a more prudent implementation is the second one because I'm not spending time creating a new thread. So I'm just spinning. Okay, so with all of this, then the question becomes, given a task set, is it RM schedulable, right? So now schedulability. So I'm modifying this. Is equivalent to saying, is it RM schedulable? Or is it scalable with RM? Okay, so that's the question we need to answer. So that's where we were, and I had sort of quickly shown some results on that, but now let's sort of walk through that. So firstly, actually, let me. One thing that we also saw was independent of rate monotonic. We saw was that response time is largest at critical instant. And does anyone remember what the critical instant of a task was? Yeah, you have to wait the longest, but when does it happen?
It comes in with all the higher priority.
Right. So when it arrives, when a copy of the task under consideration arrives simultaneously with a copy of each of the higher priority tasks. Okay, that's the critical instant. So one way I could assess schedulability is for each task I can prove that is at its critical instant it does not miss the deadline. Right? I could do that, except that's going to be quite painful because I have to kind of simulate the system basically. So the question then becomes, can I analytically show something? And that's where what we will do first. And it turns out that in many cases you can get an answer, but there is no algebraic equation which can unambiguously give you an answer. So, but let's see what we can do. So the way people approach this thing is, you said, look, what do I know about the tasks? Well, I know the C's, I know the T's, right? That's my knowledge. So the first thing we can attempt doing is intuitively what fraction of the processor a task takes. That's Ci over Ti. I can sum it up. And indeed, that whole thing you can say is the fraction of the processor that is actually going to be used by the task set. And if it's greater than 1, then obviously the task set is not schedulable. I can't have more than 100% of the processor. But if it is less than 1, we already saw that under certain circumstances, things are not schedulable. So clearly the answer is not simply saying u less than equal to 1. That doesn't work. So what does work? So let's kind of talk about it. So main limitation of fixed priority scheduling is that it is not always possible to fully utilize the CPU. Or in other words, it's not always possible to use 100% of the CPU. There are task sets where the only way to schedule them is to use a processor which is faster than the processor which would have resulted in u equal to 1. That is, if the task set results in a u which is too large, it still looks lower than 100, but it's larger than a certain number, it will fail to schedule. So I just need an excessively fast thing. It's the analogy, since I have often used the car analogy, it's like while I may need an extra powerful engine just for those moments where I need to accelerate. Or I guess another example, take your um, internet connection at your home. Your average data rate for the average amount of data that you can consume over a day divided by 24 hours is probably a reasonably low number. But while you are watching that YouTube video or playing a game where that response from the game server has to come back and all, you need a higher bandwidth, because if the bandwidth is too low, latency would be too much. So in order to meet rapid latency, low latency requirements, I will need a powerful processor. Or when we were talking about big dot little a few lectures ago, processor, remember the whole idea was a big processor kicks in when the user is doing swiping and stuff like that, right? The load is going up. So we do want that. So it turns out that even though rate monotonic is optimal, that is, if it cannot schedule it, no other static priority can, the processor bound with which it can achieve this thing is less than 1. So that is, another way of saying is, oftentimes I need an extra fast processor than what the processor utilization would suggest. So,
Which means that the other processor is also not going to be completely utilized, right?
which
Like you said that like the requirement of the second processor when your U is not exactly 100 but beyond a certain threshold. So in order to completely schedule it properly, so which means that this is also not completely being used and the second one is not also being used.
Yeah, so there does not exist a processor which you could utilize 100%. Another way of saying is the following: if I start using a slower processor, which means increasing C, which means increasing U. So if I keep the processor, make the processor slower and make it so that U becomes 1, it may not be schedulable. Okay, so I have to use an extra fast processor. If all I cared about was the rate, right? Deadlines were not a consideration. Then I can make the processor slower or pick a slow processor until U equal to 1, because I will just keep the processor fully occupied. And that's the best I can do. But because of deadlines, I need to use an extra fast processor. Okay, the question is how much extra fast? And so one result, and which is the following, that if I have a processor which is sufficiently fast so that U is less than equal to roughly 69%, then the task set is schedulable. Okay, so I can make any task set you give me with deadlines schedulable by picking a fast enough processor so that U is less than equal to 69% or so. But that's for an arbitrary number of tasks. For us, if I know the number of tasks, then the threshold rises. Okay, and we'll see shortly. Like for n equal to 3, it's sufficient to have a processor which results in 78% utilization, and so on. Okay, so there exists some some sufficiently fast processor at which you would be able to execute. So. Mm-hmm. Okay, so yeah, so perfectly, as in, yeah, they don't fail, but in particular, they don't violate the worst case execution time. Okay, if they do, we can't promise it. If their execution time is less, it will only be better. It will only be better for a single processor case. It turns out that if you're playing this game with multiple processors and your task runs faster than you think it would, it may actually result in a deadline miss. Weird. I mean, you can't intuitively think that way. That why would making a task faster would result in deadline miss? But multi-processor case is complicated. But for single processor, task may finish sooner than it promised, but it shouldn't exceed the time. Okay, and so typically what operating systems do is, if a task exceeds the time, they're going to kill it. Okay, in case of real time things. So that's how you handle it. Okay, so what do we have? The result that we have is the following: that for a set of n tasks with fixed priority assignment, the least upper bound to processor utilization is this number. What it's saying is, in kind of plainer English, is that if the utilization, the processor utilization of the task is less than equal to this number, then that task, then any task set with n tasks is schedulable. Okay, so if I take all possible task sets with n tasks and I look at which one are schedulable and which one are not, you will find that those which have utilization less than equal to this are always schedulable. And that is all task sets of size n below this are schedulable. Above this, some are and some are not. So your first test you can imagine is I apply this test and say is a task set schedulable. So to answer that, I calculate u, I check u against this threshold, and if u is less than equal to this threshold, we know that it is schedulable. If not, we have to do something extra. Now, this is for an arbitrary n, and as you make n infinity, n larger, it keeps reducing, but eventually it saturates at 0.69, so it kind of converges.
So this theorem takes into account for deadline, right?
This takes into deadline. So the promise it's making is that every instance is going to finish before the di, which is di equal to di. So basically, for our purposes, what it boils down to is that if u is less than equal to this, then we know it's schedulable. If it is not, I have to do something extra. And we'll see there is one more test, which is a better test. But in the worst case, you will have to do the critical instant check, okay, which means kind of simulating the running of the system. So if u turns out to be greater than this value and less than equal to 1, then I have to use theorem 1, and theorem 1 basically said the critical instant occurs when the task arrives simultaneously with a request for each one of these. So essentially, I'll have to imagine what will happen with the task arriving and kind of simulate the system and see whether that instance meets this deadline or not. And we'll see how you can do that simulation in an algorithmic manner. Okay. Thing to remember is that this test is valid for any priority assignment. Like I don't have to do rate monotonic. I can take any priority assignment and apply this test. So this test is more powerful because more general, but the previous theorem that we had, the previous theorem that we had, this one is only applicable to rate monotonic. Okay, so that's an important thing. Also, so only for rate monotonic assignment. Okay, so let's take an example. Let's say I gave you these two tasks, period, deadline, famous period, some computation time, and is this task set schedulable? So I calculate the u turns out to be 0.41, and for n equal to 2, that expression is 0.828, and so the foreground is very much lower, so yes, it is schedulable.
Do these fixed formulas actually work in real time? How well do they work in real time?
What do you mean in real time? In real life or in real life? Yeah, you apply this. So the thing is, you need to profile your tasks to get an estimate of the worst case execution time, and then you apply this. Okay, now what the simpler things are not showing is some of the added complexities that come into play, right? For example, time for context switch. Now it turns out that you can show that any task will only face a certain number of context switches. So you just add them to the computation time. So there are ways to work around it. So while I may not be able to go them into this course, but they kind of exist. Trust me on that. The thing is, you will probably not be using these things directly. There are design tools which analyze it for you. Okay. So outside the confines of whatever exams in this course or other such courses or kind of rough calculations. Okay, but for exact analysis, you're going to use tools which do this thing for you, and they take into account all sorts of things.
So it's not my previous question, well, so this works on the deadlines, but is that only if the deadline is equal to the period?
There is a generalization which works for arbitrary deadline. I will go through the one case of that generalization. The other case is a bit hard to explain. So okay. So at the very end, I'm going to touch upon things which you have to add on to it to make it work in real life, right? I mean, right now, remember, we are also assuming independent tasks. That's as unreal as it gets, right? So, okay. Now let's add third task to it. So this one comes every 150 time units, takes 68 time. I apply U. U turns out to be 0.86 now, whereas for n equal to 3, that expression is 0.779. So unfortunately, this means in this case, I can't give you an answer. Okay, it may be schedulable, but we don't know for sure. So now we have to see. So now we know that rate monotonic means task 1 will have the highest priority, task 2 will have the second highest priority, and task 3 will have the third highest priority. We have already shown that 1 and 2 by themselves are schedulable. So now all I need to do is to do a critical instant analysis of task 3. Now critical instant of task 3 would be that it comes simultaneous with a copy of task 1 and task 2. So now let's see mentally, let's do a mental simulation of what might happen. So since task 1 and task 2 are higher priority, they will run once each, right? So particularly at t equal to 0, if I were to start drawing, this is t equal to 0. So first thing that will happen is task 1 will run, and it will consume up to time 20. And the next copy of task 1 will arrive at this point, right? At t equal to 100. So we have time. So this is 1. Let's do task 2. So task 2 will get the CPU at this point, and it needs time 30. So that's task 2. And task 2's next copy arrives at somewhere here, 145. So we don't have to worry about it yet. What will happen to 3? Well, 3 needs 68 time units. So it will start to run out here. It will run until 100. And then at that point in time, a copy of task 1 arrives again. So the CPU will switch back to task 1. The OS will make sure of that. And task 1 is, actually I messed it up here, right? Oh, did I? Yeah. I drew 145 in. 145 is somewhere here. Okay. So what happens out here? I'm sorry, I messed it up really bad here. The 30 was up to this point. So this will get the CPU here. Okay. So that means 20 plus 30, so this is a 50 point. So this guy got to run for 50 time units. And then this guy comes, he gets a CPU. So now we are at time 120. And that's great because we still haven't hit 145, so the CPU is still free. So this guy will start running out here, and it needs to run for 18 time units. So well before 145 it will finish. So in this case, you can show that at t equal to 138, it would complete, and so we didn't have a deadline miss. So indeed the answer is, therefore it is schedulable. Okay. So what I had to do is this kind of a simulation, right? Unfortunately, there is no easy way around this thing. So any algorithm to be able to do this thing will take conceptually time equivalent to until whenever you can make a statement about it. But there are you can attempt to make it more palatable, and we are going to see that shortly. That's something what sort of tools with just such analysis do. But before that, I wanted to present one more better formula. Okay, And it's more recent, as in it appeared a couple of decades after the original formula did. And in this case, they said, instead of just knowing U, what if I rely on individual U sub I? That is, I look at the utilization of each task. And then it turns out that if given a set of tasks, if this constraint is satisfied, that is, if ui plus 1 product of those is less than equal to 2, then the task set is schedulable. And if not, we can't say. It turns out that this one covers a lot more task sets than the previous formula did. That is, it's a much more accurate way of doing the classification. Lots of task sets where the previous formula would have thrown its hand. I don't know. This one can give you an answer to that. So again, this is just an algebraic thing. You just have a bunch of UIs and you add one and you take the product. So very easy to do. So it helps things quite a bit. Now it turns out this is the best possible formula that there is. That is, if all I knew are processor utilizations, there is nothing else that you can do mathematically. So now, if we can do nothing else, so what we now have are the C's and T's. We have to do that simulation. We have to do that critical instant analysis. So let's walk through it and see if we can write an algorithm for doing that analysis. If I were to ask you to kind of write a little C program where given CI and TI, you have to say, is it schedulable? You might imagine that an operating system may have to do something like that, right? Because the thread may say, this is my CI and this is my TI, and the operating system say, can I accept this thread? That is, will letting this thread will activating this thread result in a deadline miss, right? So that kind of question an OS may have to ask. So let's see how we can kind of approach this thing. So firstly, what that OS would do is first apply that formulas that I gave you, and only if the formulas fail would they start doing this more elaborate test. So let's consider the highest priority task. For highest priority task, from the point it arrives, it immediately gets the CPU, and therefore its response time is going to be exactly its computation time. So it's going to be R equal to C. The problem comes for lower priority tasks, because what happens is they can be preempted. So let's say I take a lower priority task I, and I look at its response time. That is, from its arrival, when will it finish, then it will at least take the amount of time which is for its computation. It has to run once, and then it is going to be preempted by higher priority tasks. So we are going to call that interference, and we are going to lump that under I sub I. So I sub I is some magical variable which captures the cumulative effect of interference by all higher priority tasks. And we are going to try to quantify it, and furthermore, this interference is the one which occurs in this period, from arrival till finish, right? And when will this task finish? If it will finish at T plus R sub I, because we define R sub I to be the response time, right? So this is the interval over which we have to check things. Now remember, R sub I is unknown, right? So we have kind of a recursive situation, but let's see how we solve it. So now consider our task I, and consider some higher priority task J. Okay, and now during that period R sub I, during that interval R sub I, task J can potentially arrive multiple times. Because remember, it is a higher priority task, and in rate monotonic, if you were using rate monotonic, I would be actually giving it a higher priority, so they are also more frequent, so they may arrive. So it's possible, generally speaking, that task J will come multiple times during the period. It came at the very beginning because it's critical instant, but it may arrive additional times. In particular, number of times a particular task, this should be J. The jth task will come is R sub I over Tj and ceiling of that. The reason ceiling is because we also have the very first time. So, by the time from the arrival of task I to the finish of task I, j can occur this many times. Ceiling of Ri sub tj. And each time it arrives, since it has a higher priority, it will finish to completion. So each one of those will need C sub j time on the CPU. So total time task j will have on the CPU is this much. Number of times it arrives times the computation time. Now, of course, remember again, this thing is dependent upon R sub I, but that's fine. Just stick with that. So now what I can say is the following, that the response, the interference from higher priority tasks is a summation of terms like these. So a summation of Ri over Tj Cj over all j which have a higher priority than I. Right? Is this clear? So I'm basically saying that for every higher priority task, I'm finding how many times it came and what would load on the processor have been, and I'm kind of just adding them up. And then plugging it back into our formula, we get this equation.
So we are kind of adapting the rate monotonic to this as well.
Remember, here I did not make anything assumption about rate monotonic. All I said is higher priority tasks. So it could actually be even a non-rate monotonic assignment. But if it is rate monotonic, it's fine. All I care about is I know the TIs and whatever the T's of every task and C's of every task, and I'm basically saying for any given task I, it would have been preempted by higher priority tasks, and that's what HPI means. HPI is the set of tasks with priority greater than priority of I. Okay, so I'm just sort of adding them up, and now for ith task, the response time Ri is therefore this expression. And what is our goal? Our goal is to show that that for ith task to be schedulable, R sub I should be less than equal to T sub I, right? So or more generally deadline I. So so we have to find a solution to this thing, and in particular, we have to find the smallest value of Ri which solves this equation.
This equation, so you have R sub I in summation as well. And
yeah. So I don't know if you've ever seen in any prior course, but equations of this form, x equal to fx, where f is something non-linear, okay, because we have this weird ceiling function, right? They are called fixed point equations. And the way you solve them is iteratively. How many of you have seen equations like these ever? You have, right? Okay. No one else? Never? Okay. Well, they exist. Okay. So the way you solve them is numerically. Because obviously we can't do them analytically. The way you solve them is numerically, and the approach is very simple. You make a guess and we iterate. So we start. Let's assume x is this. Calculate the new x using this equation, and then take the new value, feed it back until the thing converges. And if your guess was wrong, you try a different value. Okay. Now, turns out this particular case has a nice property that it's a convex function, so you will always converge that. Okay. But in general, your function would have weirdo behavior, in which case things can be off. But this is a nice case. Now, I know for sure that my response time is at least C sub I. In fact, it's at least C sub I plus the C's of each one of the higher priority tasks. So I have a reasonable good guess for the initial value. So what this equation you're seeing is an attempt to solve this fixed point equation iteratively, where the initial solution would be Wi0, and then this n is not representing power; it is representing the guess number. Okay, so we start with a guess number 0, calculate guess number 1, keep iterating until one of two things will happen. Either I will end up with showing that it is not schedulable, because if you think about it, with this, my guesses will only increase in value, right? Everything is positive. So So I may end up with a situation that my guess is still hasn't converged, but it has become larger than my deadline. Then I can give up. Or it may converge, in which case I have my solution. Okay. So this particular equation is reasonably well behaved. So one of the two things will happen. It will either keep increasing and exceed the deadline and then you stop, or it will converge, which means you will find at some n we will see WIN is the same as WIN plus 1, and then you can stop. So, so that's kind of the basic idea. So it will either converge or become greater than deadline. In either case, I can stop. And all of this we can encode into kind of nice pseudocode, which is what I'm doing. So I initialize a value and then kind of look through it. It's literally this thing, but what you would see out here is two cases. If it is greater than the deadline, then that means scheduling fails. And if it has converged, so this is convergence, and this means greater than deadline. So the two cases, and since our equation is such that f of x is strictly greater than x, is at least is greater than equal to x. So again, the property we have out here is, in our case, xn plus 1 is greater than equal to f of xn. That property holds true, and therefore kind of a well-behaved mathematical function. 2 minutes? Okay. So generalization of this, what if the deadline was not arbitrary, not equal to ti? Well, the case where deadline is less than ti, you can apply the same formula, same approach. All you do is you replace this ti by di. Rest will still work. What about if we were to, but the question becomes, what can we say about the priority? What priority should we pick? And the answer there is also very simple, that we replace rate monotonic by deadline monotonic. Basically, we say that those which have a closer deadline, we give them a higher priority. Okay, so now this only works for di less than equal to ti. Okay, for the case that di is greater than ti, that is, I'm willing to wait longer than the next arrival of the next instance, unfortunately, there's no result. Okay, so for the case no result for assigning priorities if di is greater than ti. All you can do is try all orders, all possible factorial n ways of assigning priorities, and check. Okay. So case di greater than ti is pretty problematic. So for example, if these were my tasks, they have period 20, 15, 10, and 20, and their deadlines are 5, 7, 10, and 20, rate monotonic would have said task 3 gets the highest priority, whereas deadline monotonic will say task 1 gets the highest priority. Okay, because now in this case we have to use deadline monotonic because my deadlines are not equal to the period. So final bit, complications. So one complication that arises is that importance and short deadline are not the same thing. So what we have done here is, in rate monotonic and deadline monotonic, what we are doing is we are saying closer the deadline, higher the priority. But I may have tasks which whose period is a rate monotonic, or whose deadline may actually be more relaxed, but they're more important. I would rather that they not fail. So so important tasks may have long periods, and therefore when CPU gets overloaded, they may be the first one to fail. Because when CPU gets overloaded, it will be the lower priority tasks which may get starved out, but they are the ones which are important. If they happen to be the ones important, then it's a problem. So that's one issue with this framework, that importance versus rate, these are two different concepts of priority. What if tasks were not exactly periodic? What if they were arriving with a jitter? It happens a lot of time. If sensor was on across a network, and so the sensor messages were coming over a network like our CAN bus, by the time they hit our CPU, they may not exactly be periodic. So the answer turns out to be that you add a jitter factor into the formula. What if the tasks are sporadic? That is, not every period the task actually arrives. What it arrives on some fraction of them. Again, there is some theory to deal with this. This is an important one. What happens if the tasks are not independent? What if they interact with each other? What about tasks that can lock out the interrupt? They disable the interrupt for some time. Tasks deadline greater than period. I already said no known riddles. What about processors switch to power management? They can shut down. In embed, when you call the wait under certain circumstances, it can put the CPU into a standby mode. So now when the task arrives, it may take some additional overhead to reactivate the CPU. And finally, many embedded chips now have multiple processor cores. What should I do? Should I now have an additional problem? I have to map the task to a processor core also. So there are all these complications which obviously sort of research has addressed most of them, or they have found that there is no answer. I'm not going to go into those because many of them are not relevant to us. But solutions exist for this problem, this problem, this problem, this problem, and this problem. All of these are have been addressed in research. So I'm going to leave it at that, and so I'm going to see you guys next Thursday, and next Friday's discussion section is again turned into a lecture, and Amr is going to do a 2-hour discussion section on Tuesday. I need to make maximal use of it. Firstly, bring the hardware, and secondly, attempt the homework before that so that you can ask questions.